Hello everyone. Uh, this PPT is part of an FDP program. It's a mandatory e-content that is to be delivered. Uh, so the title of the FDP was Digital Manufacturing and Industry 4.0, and what I'll be presenting is how 3D printing, which is one of the technology enablers for Industry 4.0, I mean, among the many other technology enablers, for example, augmented reality and artificial intelligence and machine learning, and even blockchain technology. How 3D printing is also I'm sorry, is also a technology enabler for Industry 4.0. Okay, so so Industry 4.0, as we know, is generally called as the fourth industrial revolution. We had Industry 1.0, Industry 2.0, and Industry 3.0, and all of them were aimed for different objectives. They were only aiming at different objectives. But Industry 4.0, as we know, is for mass customization. That's the buzzword, or that's the essence of Industry 4.0. That we are aiming for mass customization, not for mass production, which we had in the earlier or the previous revolutions. We can say we are aiming for mass customization, and that is we are trying to it attempts to connect the direct and indirect manufacturing activities through data exchange and automation. So we already had in IT technology being used for manufacturing activities to accelerate or to enhance the manufacturing activities and to mass produce components. But here in Industry 4.0, we are trying to have an integrated data flow between all the activities, direct and indirect, meaning the business functions as well, the sales as well. So that is what we are trying to do to aim for mass customization. This is what we are essentially doing, that we are trying to connect all the activities, direct or indirect, right from the sales and even to while the components are going in service, getting the data from the service data is also part of the decision planning that goes on for any manufacturing activity or any design activity, R&D of any product. And to serve the variety in customer preferences, the design features in products and consequently the manufacturing activities have to be customized for the realization of the product conceptualized by the customers. So if we are to uh, give weightage to the customer preferences, each customer has its own preferences. So to accommodate all those design features in the products, the activities have to be different because the features require different activities, manufacturing activities. So that to serve the variety, you have to have uh, a customization in the activity manufacturing activities. If we are to uh, give weightage to the customer preferences, so that's a natural consequence. While Industry 4.0 ensures mass customization with the help of cyber physical systems, right? Uh, that's a keyword in Industry 4.0, that you have cyber physical systems, meaning the physical systems have connectivity with the other systems as well and with the other departments as well. And cyber physical systems and 3D printing, that's what I'll be focusing on. Other technologies as well, we have IoT, Internet of Things, as we know more commonly. It's a general word. Augmented reality, artificial intelligence, and machine learning, they all support this, or as I said, they act as enablers for the different business functions and practices. On the roadmap of Industry 4.0, additive manufacturing or 3D printing have a key role. Why? Because it helps to achieve sustainable manufacturing. This is another goal that we have kept, a uh, global goal, we can call it, that we want to aim for sustainable manufacturing, near to zero wastage. We want to have less impact on the environment, so that the future generations can also have the same, or if not the same, similar, uh, they enjoy the similar resources that we do. So efficient material utilization, resource utilization, and less impact on the environment is what is sustainable manufacturing, while reducing lead times also with the help of rapid prototyping for swift product development cycles. So this is the crux of the 3D printing, that we are one of the applications of 3D printing or one of the applications of rapid prototyping technology is 3D printing. So if we were to talk about 3D printing, then we would say we'd use 3D printing for rapid prototyping, which of course we know, as we know, 3D printing is having lesser material wastage, near to zero, we can say, except for some post processing material wastage. But because we are adding layer by layer, we are not removing material, as opposed to subtractive manufacturing. Therefore we will have less wastage, and therefore swift product development cycles. We can have rapid prototypes, which will help us to accelerate the design cycle. So that is where the product development cycle is affected because of 3D printing, and that's how it affects sustainable manufacturing, as well as I explained. Now, to dive into rapid prototyping, how 3D printing, I'm connecting how Industry 4.0 is connected to 3D printing, and 3D printing is now helping us for rapid prototyping and reducing the product development cycle. Now, the concept of a prototype, as we know, what's a prototype? It's a model fabricated to prove out a concept or an idea that we want to either prove a concept, or we even want to test its functionality, right? So there are different prototypes: conceptual prototype, functional prototype. So starting with conceptual mockups and building towards a functional prototype, each successive prototype is a step towards a fully engineered final design. That's prototyping. That the cycle, as you can see, a prototype is developed, it's reviewed, you refine and iterate it, right? Once the review is done, either you decide if it's all good, it goes to delivery, which is a very rare case. It has to go through iterations, so that we can accommodate all those changes, or the modifications as required, keeping in mind the customer specifications and the technical feasibility as well. So if it's not well and good, we go for refine and iterate, and then the same cycle continues. This is rapid prototyping. You have to uh, quickly iterate, right, so that you can deliver. That's rapid prototyping. This is the concept of rapid prototyping, and we know this, that if this cycle, right, this all the iterations, if it can be streamlined as soon as possible, that's called rapid prototyping. You don't want to have much time wasted on the prototyping, and the design phase has to accelerate if we want to go for production quicker. So the discovery of the the conceptual ideas, if they have to be materialized and seen for feasibility, you have to have a accelerated prototyping process. So that's how it is: discovery of an idea, concepting, and then it goes to production. That's the usual prototyping stages we have. And why do we need to compress the product development cycle? That's another question. Why should we have lesser product development cycles? Because we know there are a lot of bottlenecks, as I said. Either the technical feasibility, or whatever is the customer demanding is not possible as per the manufacturing facilities or the manufacturing technology we have. Or it may be that the cost goes on very high, which is not acceptable to the client. Then you have to have changes again. So to bring about those changes and to effectively convey to the customer or the client, you have to have prototypes being produced faster. Otherwise, if you have to go for a traditional method of making a prototype, which is our conventional subtractive manufacturing, wherein we remove the material, that will take time, as we will see. Forestalling or delaying one major bottleneck, which the bottlenecks that we discussed, that happens on the way to final product design, can make the entire process better and faster. So you have to either forestall it or delay it, and so that we can make the entire process faster. uh, Traditional prototyping, why is it a problem for us? Because it requires that a new design be outsourced to manufacturers. Any change in the design has to be outsourced to the manufacturers. What they will do, they will do it's a practice processes generally, lengthy waits and costs, the tooling and logistic in each design step. So tooling and logistic will come into play every time we are making a change in the design. So that is where the time increases and the cost as well, because you have to invest for the tooling and logistics and the R&D that goes in at every step. So the feedback from each step is not translated immediately. This is the problem with traditional prototyping. Immediate transfer of feedback is not possible with conventional and traditional method of making prototype. So those changes to make it the product features are not incorporated quicker. So this is where we want to. This is the usual condensed design cycle. We have concept development to system level design, and then we go for a detailed design, and then testing and refinement, and then the production ramp up. So to be able to accelerate faster at each and every step, you have to have a faster prototyping mechanism, so that we can incorporate the changes whichever are there, which will be very much there at every in every product development cycle. You have to have a rapid prototyping process, which is possible through 3D printing. That's where I'm going at. So this is general product development flow. As I told you, the different bottlenecks we'll have at these steps. These are the steps where we'll have bottlenecks. You have the generation of ideas, basic bill of materials you'll create based on whatever concept you have done, basic business plan, how it is going to survive, and uh, the economics of it, and then doing a business case review for determining the feasibility, whether it is feasible to produce in so and so amount, and then can we make profit out of it, or is it feasible in that sense. Developing the concept, and then you perform DFMEA, design for failure mode effect analysis, uh, detailed business plan. So it's streamlining now. Design engineering, the engineering hand calculations, right? The theoretical part, and then CAD and FEA for the simulation part. We make models and then we analyze or predict the product behavior, and then analysis in computational fluid design. This is a usual thing for aerodynamic and other applications, but even structural analysis and all can be seen as general analysis. And mathematical modeling and multi-domain simulation, if it's multi-physics, then you have to go for that. Prototype development, testing and design validation, and then the product validation. That's how product developments flow general for new products. So to avoid bottlenecks in every step here, you have to have faster prototyping process, and that's where 3D printing helps us. So how this product development of an orthosis, for example, just to give you an idea of what product development looks like for any particular product. We are scanning 3D scanning and interactive geometry placement. So that we are trying to scan. This is patient specific. This is a medical case study that you have to have specific product suited for a particular customer or patient. In this case, you scan the data using a 3D scanner. You get the data, scan data. This is a uh, this is a computer model that we'll get, and then we are trying to develop a orthosis, right? That's support for the patient. So you are seeing how the movement of the face, or the head, will affect or cause stresses at different points of the orthosis, that supporting orthosis, we can call it. So that how that is affecting, how the movement of the head is affecting different points of the orthosis, and how we have to model the geometry, how we have to uh, keep the geometry where the hole should be placed, so that the patient is not uneasy when he uses that product. So to be able to do that, you have to see the different stresses generated at different positions, and how can we better accommodate those movements in terms of geometry that we are keeping, and the material as well. So that now they have gone for, instead of making one full, they have gone for four different pieces, or more, four or more, four I think here. So that is how they were able to produce that. So simulation as well was carried out, as you can see, to check the stresses, to predict the stresses, and then they went for a final 3D printed part so that we can have that final product. Why rapid prototyping? As I said, to decrease development time, to increase effective communication between the team members, the design team, or even the production and quality team, because this is concurrent engineering we're talking about these days. Uh, to decrease costly mistakes, right? Because if it at a later point of time, if it's known that it is not feasible or it's costly, I mean costlier to make, then you'll have to again go back to the first phase. So to be able to avoid those mistakes, you have to have a good prototyping mechanism to minimize sustaining engineering changes, right? So engineering changes, we have to minimize sustaining the engineering changes. So if there are changes to be made, we know this is I mean it's a faster, the pace of development or the pace of launching new products is now very quick. So to be able to do that, you have to have uh, good rapid prototyping, as I said, to extend product lifetime by adding necessary features and eliminating redundant features early in the design phase. So in the design phase itself, you want to sort out everything so that very less problems occur in the manufacturing phase, and if at all they can be sorted out. But major changes, if any, then you have to have. Uh, I mean, it'll be a, it'll come at a cost. And then this is a video. I hope this will not play. So let's go to the next slide. A case study how that 3D printing helped the GE Catalyst engine to reduce even the fuel burn, the fuel consumption was reduced, and the number of parts, because 3D printing, as we know, is it reduces the uh, assembling of parts, because we are making complete product. So 855 parts to 12 parts, right? So that's how they were able to reduce the number of parts as well, and the weight reduction 5%. So that's how. So all of this you can see, right? The different parts are now being integrated to one part, kind of that. This was the component produced from 3D printing direct. So seven assemblies to one, 300 parts to one, and of course these are the that's the weight reduction is the one uh, significant aspect that we get when we use 3D printing technology. Then in manufacturing industries, we have to increase the number of variants in the products. You have to have a lot of variants in one single launched product. Product complexity is increased, right? To increase the complexity and to have more features involved, you have to have uh, this kind of swift product development cycles. To decrease the product lifetime before obsolescence, decrease in product lifetime before obsolescence. So you have to have, the lifetime of the product is now very less, uh, because the products are being launched one after the other. Decrease in delivery time, you want to decrease the delivery time, there is a lead time. Product development by rapid driving by enabling better communication. That's how I do. That's what I said. In the design team, you have to have good communication, even the design team and the management team as well. So why not just conventional machining? Because of all these reasons. Difficult to machine, complex shapes, right? Difficult to machine concept complex shapes, because some shapes are not at all possible with conventional. That's the different holes, right? If it's a straight drill, then it's possible. But if it's a spiral kind of drill, a spiral or channels, cooling channels, if you're talking about in the engines, then these are not possible with conventional machining. Time consuming. Conventional machining is time consuming. We know it's costly, tedious, very laborious, right? Because a lot of operations have to be performed one after the other. Skilled operator is required for that case. Even if in terms of CNC, you have to have an operator who knows how to operate a CNC, and the complex uh, uh, geometry requires complex functions. Lesser accuracy, yeah, there is some, and even the increased product development time, as we were discussing. What is the methodology of additive manufacturing? You have a CAD model, you construct a CAD model, that's where it starts, and then you convert it to an STL format. Basically, a triangulated, I mean, it converts a solid model into a uh, sliced model, if you were to say that way here. A machine processes .stl file by creating sliced layer of model, right? Basically, we have triangles of, I mean, it tessellates it in the technical terms. You have one solid object being converted into small pieces so that the computer can understand, or the printer can understand, what data is at each layer, where to solidify or melt at the different cross sections, so that the slice layer will have the data. I'm sorry, the STL file will have the data in terms of the sliced layer. First layer of the model is created, and then the model is lowered by thickness of one layer, and then the process is repeated. If it is a melting process, the laser melts it. If it is a binding process, there is a resin added. So it depends on different technologies, but that's how it goes. First layer, and then the model is lowered. The second layer comes, and the operation is performed, and then it is lowered again, so that the model is built layer by layer. The completed model and any supports are removed. If there are supports required for overhanging parts, then the supports are removed. Surface of the model is then finished and cleaned. So the finishing and cleaning. So that's how it is. Input. If you want to talk about physical objects, because if you want to 3D scan it, then you have physical objects as the input, and a scanner is required. CAD models, STL files, slice model files. These are the inputs. Material. In terms of material, all these materials are possible. In terms of liquid, powder, or solid, that's a general classification. Paper, resins, nylon, ABS, wax, metals, ceramics, almost all kinds of materials that we have are possible in additive manufacturing. I mean, to be able to print, 3D print them. Methods, you have photo curing, cutting and gluing, melting and solidifying, binding, etc. Applications, design, we have applications, engineering analysis and planning, manufacturing and tooling as well, because we can even create tools on spot, so that you don't have to wait for the tool to get manufactured by the traditional means. You can create it there and then. Tool as well, fixture as well. This is a good application that we are using in manufacturing industries. Applications, you have in the design phase, you have CAD model verification, visualizing the objects, as I said, visualization, proof of concept, market and presentation application, if you want to present it in the market, how it looks like and feels like. Engineering analysis and planning, form and fit, right? How to check the form and fit, stress analysis, mock-up parts, even the interface analysis in the form and fit category, how the different parts are interfering with one another. If you want to see that, because there are many parts involved, it becomes complicated. So to be able to check the compatibility of different components, you have to have a prototype, pre-production parts as well, before going for a full-on production. Diagnostic and surgical operation planning. This is another use case in medical, where they are using for pre-planning of the surgery, that the doctor is able to see how the actual uh, that the operated thing is like. Manufacturing and tooling, as I said, tooling, mold parts, soft tooling, and hard tooling. Basically, you create a tool, and then based on that, we do 3D printing one component, and then with that component, you create a mold so that it can be used again and again. Casting, EDM, electrodes are also being 3D printed, uh, and master models as well. Applications, you have aerospace, automotive, education, biomedical, jewelry, consumer, electrical and electronic products. So just as an example, this is for medical students to show how it looks like, how a heart looks like. So you can 3D print them. So that's where in the education sector as well, 3D printing is being used. And these are the different case studies that, with the help of 3D printing technology, basically SLM, I believe they have used. Uh, this is a metal product. This is a 3D printed metal bracket by Rolls Royce. So even the QR code and part number they had printed on the component, so they were able to print even that. So an additional process is not required. If it comes to conventional, you need to have an additional process, but here it's not required. The 3D printer can take that as a layer information to even print the QR code and the part number on the part itself. In the automotive as well, for to create that hub, the complicated hub, to 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 avoid those complicated millings and everything, you they basically produce this 3D printed upright. You can see the geometry also. We can have the design space, the design freedom that we get with 3D printing is also another useful. Uh, is a significant. Uh, it is also of significance. that even the material is reduced because of these things, that you can have geometries which are not possible with conventional means. You cannot produce this kind of component in conventional way of subtractive manufacturing, for example, or even forming, etc. Architecture, these are all examples, right, for visualization and presentations, and to basically for the even the architect to have a look and feel of the product, or the design that he's planning. In the food industry as well, this is a common thing now, that they print whatever they want to, whatever the color they want the food in, especially for children, right? So this is food industry being utilized. The food industry is also utilizing 3D printing. Aerospace, we know this is another major sector. Aerospace and medical, these two are sectors where 3D printing is used a lot, because if you want to reduce the weight, the aerospace is utilizing it for that reason. The weight as well, and the time as well that is required. Of course, it comes at a cost, and aerospace industry is ready to pay for that cost. Even the consumer industry, right? Material addition, either liquid or discrete particles. So you have all these technologies. Uh, and if you want to if you want to name specific technologies, then we have specific laser sintering, 3D printing, as we know generally, and even FDM, fused deposition modeling, and solid ground curing. So all these are under liquid, uh, if you want to classify that way. And finally, if you want to look at the prototype fabrication techniques, then if it was in terms of subtractive, we had all these things: laser cutting, water jet cutting, EDM, electric discharge machining, EB, and CNC machining as well. So these are all subtractive methods of manufacturing a prototype, creating a prototype. And in terms of additive, you have SLA, selective stereolithography, selective laser sintering, fused deposition modeling, and direct casting. And in terms of formative, you have all these things. So there are some common points as well. So and the lastly, if it is AM classification that you are looking for, in terms of solid, powder, or liquid, then the basic processes are highlighted here. In terms of liquid, you have liquid polymerization, basically liquids sticking to one another so that you have a final product. And this is stereolithography where it happens. Solid ground curing is also relying on liquid polymerization. Selective laser sintering and 3D printing are relying on a powder, material powder, and then you bind the powder with the help of some binding agent, so that a solid model is created. In terms of solid, you are gluing the sheets either, or melting and solidification, as in fused deposition modeling. You melt that polymer, and then each layer is now joined to another by with the help of fusion. And layer, this is how one layer is created, and the other layer is created again. So laminated object manufacturing also, you have gluing of the sheets. So that's about the that's it should be a good introduction to how 3D printing is a technology enabler for Industry 4.0. Thank you.